Hello and welcome back to Discrete Mathematics. My name is Qi and I will be your e-tutor this week. Let me begin with a recap of Chapter 9, which is about functions. A function f from the set x to the set y assigns every element of x to a unique element of y. Here, every element and unique element are the crucial characteristics of a function. So f will not be a function if it does not assign some elements of x, or it assigns more than one element of y to an element of x. So in mathematical notations, we write f colon x right arrow y to indicate that f is a function from the set x to the set y. And we write f of x is equal to y to indicate that f maps the element lowercase x in x to the element lowercase y in y. So here, this capital X, which is a set, is the domain of the function. The capital Y, which is also a set, is the codomain of the function. The lowercase y here is referred to as the image of x under f, and this lowercase x is referred to as the pre-image of y under f. So the notion of images and pre-images extend to subsets of the domain and the codomain. So if S is a subset of the domain X, then f of S is defined as the set consisting of values of f of S, where S are elements of capital S. And this set here is referred to as the image of set S under function f. Similarly, if T is a subset of the codomain Y, then f inverse of T, which is defined by this, consists of elements S in X such that f maps S to a member of T. And this set here, f inverse T, is referred to as the pre-image of the set T under the function f. The range of a function f corresponds to the image of the entire domain X. Equivalently, the range of f can be understood as those elements in Y which has a non-empty pre-image. The two most important properties of a function are injectivity and surjectivity. So injectivity is also known as one-to-one, and surjectivity is also known as onto. So the function f from a to b is one-to-one if for two elements x1 and x2 from its domain A, f of x1 is equal to f of x2 indicates or implies that x1 is equal to x2. In other words, a one-to-one function, if f is a one-to-one function, then distinct elements of the domain will be mapped to distinct elements in the codomain by this function f. And f from a to b is onto if for every element y of the codomain B, there exists an element x in the domain A such that y is the image of x under f. So in other words, every element in the codomain has a pre-image. A function that is both one-to-one and onto is called bijective. And a bijective function is also referred to as bijection. Now let me introduce the notion of function composition. So let f be a function from the set A to the set B, and let g be a function from the set B to the set C. Then g compose f is a function from the set A to the set C that maps every element A into g of f of A. So you apply f first, and then you apply g to get the image of A under this g compose f. So here are some properties of function composition. First of all, it's important to remember that function composition is not a commutative operation. So in general, for two different functions, g and f, g compose f and f compose g are two different functions. The second property is that if f and g are both one-to-one functions, then g compose f is also a one-to-one function. Similarly, if both f and g are onto functions, then the composition g compose f is also an onto function. Next, I will introduce the notion of identity function and the notion of inverse function. So an identity function IA is a function from the set A into set A again, which maps every element x of set A to x itself. And now let me talk about inverse functions. So here, let f from set A to set B be a bijection, so a bijective function. Then it has an inverse function, f inverse, denoted by f with a superscript -1. It's a function from the set B back to the set A, such that it maps the lowercase b to lowercase a if b is the image of A under function f. So there are a few properties. First of all, f inverse is also a bijection or a bijective function. The second property here is easy to verify. It says that f inverse compose f is equal to the identity function in set A. And the composition of f and f inverse gives the identity function in set B. And we will verify this property in question 9 of the tutorial. Before I finish the recap, I will mention 3 topics that are related to functions: the ceiling and the floor functions, the pigeonhole principle, and the countability of sets. So the floor function, denoted by this notation, maps is a function from the set of real numbers to the set of integers, and it maps every real number x to the largest integer n such that n is smaller or equal to x. Similarly, the ceiling function is denoted by this notation. It's also a function from the real numbers to the integers, and it maps a real number x to the smallest integer n such that n is larger or equal to x. The pigeonhole principle relates functions and the cardinality of sets. So if f is a function from the set A to the set B, and the cardinality of A is larger than the cardinality of B, then the pigeonhole principle states that f cannot be one-to-one. In other words, there exist two elements A1 and A2 from the domain A that are distinct and have the same image under the function f. And the reason why the pigeonhole principle holds is very intuitive. Because if for f to be a one-to-one function, distinct elements need to have distinct images in the codomain. However, if the codomain has fewer elements than the domain, then this obviously cannot occur. The last topic today is countable versus uncountable sets. So a set A is called countable if there exists a bijective function f that maps the set A to the set of natural numbers 1, 2, 3, etc. And here are a few examples of countable sets. So every finite set is countable. The set of natural numbers itself is countable, and the set of integers is countable. The set of rational numbers denoted by Q is countable, and so does the Cartesian product between two copies of rational numbers or two copies of natural numbers or integers. And here are a few examples of uncountable sets. So the most famous example is that the set of real numbers is uncountable. And we have shown this in the lecture via the Cantor's diagonal argument. A related uncountable set is the set of irrational numbers, or real numbers minus the rational numbers. And here is another example of an uncountable set. So it's a set of functions from real numbers to real numbers. This set is also uncountable. In question 1, we consider a set A with three elements, A, B, and C, with power set P of A and the intersection function. So for in the intersection function for two given subsets of A, so members of power set X and Y, f of X and Y gives the intersection of X and Y. So the domain and codomain of this function are given here. So the domain is equal to the power set of A, Cartesian product, the power set of A. And the codomain is equal to the power set of A. Regarding its range, we first recall that the range of a function corresponds to the elements in its codomain with a preimage. And since we know that for any x in the power set of A, if we take f of x and the set capital A itself, we get the intersection of x and A, which is again x, because x is a subset of A. Because of this, we have that the range of function f is equal to the power set of A. Now let's consider the cardinality of the preimage of this element, the set containing a single A. So the preimage of this element corresponds to those elements in the domain of the function that are mapped to this set. So what we do is we can enumerate those members in the domain that are mapped to this. So we have this set with A intersect the set of A, B, C is A. And similarly, we can do this for AB and AC. And notice that since we are dealing with the intersection operator, we can swap the order of intersection. So we get the next three examples as follows. Next, we also have the intersection of the set containing A and B, and the set containing A and C is also the set containing only A. And similarly, we can swap the order. And finally, we have a trivial example. So the set containing only A intersect with itself gives the set itself. So in total, we have 9 elements in the domain of the function and no more. Therefore, the cardinality of the pre-image of this element, this set containing only A, is 9. In question 2, we show that the sign function from the set of real numbers to the set of real numbers is not a one-to-one function. So recall that a function is one-to-one if distinct elements in the domain have distinct images. In the case of the sign function, we have sine of 0 is equal to 0 and sine of pi is equal to 0. Since we know that sine of 0 is equal to sine of pi, which is equal to 0, but 0 and pi are not equal, sine is not a one-to-one function. In question 3, we show that the sign function from the set of real numbers to the set of real numbers is not an onto function, but if we change the codomain to the interval from -1 to 1, then it is an onto function. First, recall that a function is onto if every element in the codomain has a pre-image. So since sine of x is between -1 and 1 for any x, if we consider -2 in the codomain, we will find that -2 does not have a pre-image. Therefore, sine them from real numbers to real numbers is not onto. However, if we restrict or we replace the codomain by the interval from -1 to 1, then this function is onto. Since for every y that is between -1 and 1, there exists x between -half pi to half pi such that sine of x is equal to y. And actually this x is given by the arcsine function, or the sine inverse arcsine of y. Because of this, the sine function from the set of real numbers to the interval -1 to 1 is onto. In question 4, we check this h function from the set of integers to the set of integers given by h of n is equal to 4 times n minus 1 is onto. And the idea is that Hn is equal to 4n minus 1, which is congruent to 3 mod 4. So obviously it cannot be onto because it will not have a pre-image unless it is also congruent to 3 mod 4. So the counterexample so first I will answer H is not onto, and the counterexample is given by 1. So 1 is in the codomain, but if we let Hn, which is equal to 4n minus 1, equals to 1, then n will be equal to half, which is not an integer. So 1 does not have a pre-image. And as a result, the H function is not onto. In question 5, we check whether the cube function is a bijection or a bijective function. So recall a function is a bijection if it's onto and one-to-one. So let's first check whether it is one-to-one. So if f of x1 is equal to f of x2, which means that x1 cube is equal to x2 cube, this implies that x1 cube minus x2 cube is equal to 0. And then we can do the factorization for the left-hand side. We get x1 minus x2 times x1 squared plus x1 x2 plus x2 squared. So the product of these two terms must be equal to 0. So we have two cases. So case 1, x1 minus x2 is equal to 0, which implies that x1 is equal to x2. And then in case 2, we get x1 squared plus x1 x2 plus x2 squared is equal to 0. To see what this leads to, we will do a reformulation of this. So since x1 squared plus x1 x2 plus x2 squared is equal to x1 squared plus x1 x2 plus a quarter of x2 squared plus 3/4 of x2 squared. And then we can reorganize this into the sum of two squares. So it becomes x1 plus half of x2 squared plus 3/4 of x2 squared. And since this term must be equal to 0, we have they must be both 0. So this must be 0, and this must also be 0. So from here we can deduce that x1 is 0 and x2 is 0. In both cases, x1 is equal to x2. Hence, f is 1-to-1. And next we need to show that f is onto. So for any y that is a real number, one can take x equal to the cube root of y, such that f of x is x cubed, which is the cube root of y cubed, which is y. So we have shown that every element in the codomain has a pre-image. Hence, f is onto. Since f is 1 to 1 and onto, f is a bijection. Question 6 is about the composition of functions. So here we have two functions, f and g. And f is a function from real numbers to real numbers defined by f of x is equal to x squared. And g of x is given by x plus 5, where g is also a function from real numbers to real numbers. So g compose f is composition of g and f. Of x is by definition g of f of x, which is so x squared, so g of x squared, which is x squared plus 5. And f compose g of x, so here g will be applied first and then we will apply f. So it's f of g of x. So it will be f of x plus 5, and this is equal to x plus 5 squared, which is x squared plus 10x plus 25. So here you can observe that the composition is not necessarily commutative, because g compose f and f compose g are different functions. Question 7 is also about composition of functions, just like question 6. So here we again have two functions, f and g, but they are functions from the set of integers to the set of integers. So let's repeat what we did in question 6. So g compose f of n is equal to g of f of n. And since f of n is n plus 1, we get this is equal to g of n plus 1, which is equal to n plus 1 squared, and n squared plus 2n plus 1. And f compose g of n is equal to f of g of n, and this is equal to f of n squared, which is equal to n squared plus 1. So far in the tutorial, we have only encountered functions that are specifically defined. Here, however, in question 8, we have two functions that are not explicitly given. So we have two functions, f and g. So f is from the set x to the set y, and g is from the set y to the set z. And the question here is, if the composition of g and f is a one-to-one function, then is it possible that either f or g fails to be one-to-one? So let me begin with some ideas. So the first thing to realize here is that f has to be one-to-one. And the reason for this is that if f is not one-to-one, then there exists x1, x2 from the set X such that x1 is not equal to x2 and f of x1 is equal to f of x2. Then, if you look at G compose F now, you see G compose F of x1 is equal to G of f of x1. And since f of x1 is equal to f of x2, we can replace it. We get G of f of x2, which is G compose f of x2. And G compose f cannot be one-to-one. So f has to be one-to-one. But how about G? G actually doesn't have to be one-to-one. But why? The idea here is that G can fail to be one-to-one outside of range of f. So now let's first give the answer. The answer is no. And now we need a counterexample. So in this counterexample, let X be the set of real numbers that are non-negative, so including 0. And we let the set Y and the set Z be set of real numbers. And then let f of x be given by x. I mean, here f is 1-to-1. And let g of x be given by x squared. So here g is apparently not 1-to-1. Right? Because x squared and the square of x and the square of minus x are the same. So g is not 1-to-1. However, what is G compose f? So it will be a function from x to z. So it will be from r plus to r, and G of f of x is equal to G of f of x, which is G of x, which is x squared, and G compose f is 1-to-1. So here we have functions f and g. F is 1-to-1, g is not 1-to-1, but their composition, G compose f, is 1-to-1. So this is a counterexample, and it shows that the answer to this question is no. Question 9 is about an important property of the inverse function of a function. So what we want to show here is that the composition of the inverse function and the original function gives the identity function in the domain, and the composition in the other way around will give you an identity function in the codomain. So let's try to show this. So for any x in the set x in the domain of the original function x, we can let y to be equal to f of x. So y is the image of x under function f. And then, because of the property, due to the property of the inverse function, we have f inverse of y is equal to x. Hence, f inverse compose f of x is equal to f inverse of f of x. So f of x is y, so it's f inverse of y. This gives x. So this is equal to ix of x, right? So that's the identity in the domain. Now to show the second identity, let's take any y from y and let x be f inverse y. So x is the image of y under f inverse. And then, since f is an inverse function, we have f of x must be y. Hence, the composition f compose f inverse of y is equal to f of f inverse y, which is equal to f of x, which is equal to y, and this gives the identity in y. And we are done. Question 10 is about the ceiling function. So recall that the ceiling of x is equal to the smallest integer that is larger or equal to x. So with that said, it is very easy to come up with a counterexample to this identity here. So for example, let x be 0.4 and y be also 0.4. Then the left-hand side of the equation is the ceiling of 0.4 plus 0.4, which is the ceiling of 0.8, which is equal to 1, because it's the smallest integer larger or equal to 0.8. However, the right-hand side of the identity is equal to the ceiling of 0.4 plus the ceiling of 0.4, which is equal to 1 plus 1, and it's 2, and it's not equal to the left-hand side. And therefore, this identity does not hold. Question 11 can be solved via a direct application of the pigeonhole principle. So here we are picking 5 cards from a deck, and we want to show that at least 2 will have the same suit. So the key here is there are 5 cards and 4 suits, right? Only 4 suits: heart, diamond, spade, and clubs. So here the pigeons are the cards and the pigeonholes are the suits. 4 suits. And since 5 is larger than 4, at least 2 cards will have the same suit, will be of the same suit. Finally, question 12 can again be solved easily via a direct application of the pigeonhole principle. So here we have 10 black socks and 10 white socks, and we want to show that if we pick 3 socks randomly out of these socks, we can always find a matching pair. So here the pigeons are the 3 socks that we randomly pick, and the pigeonholes are the 2 colors, black and white, right? And since 3 is larger than 2, there will always be two socks among the 3 with the same color. And are thus matching.